In this video, we're going to take a look at the behavior of graphs, and we'll also talk about how to use technology to help us identify important features that graphs have. So first we'll look at the concept of when a function is increasing and when it is decreasing. So the formal definition says that f of b is greater than f of a for any two input values where b is greater than a. Okay, if that's true for all the values on an interval, then it's increasing on the interval. Okay, but I think what's most effective here is if we just draw a quick picture of what's going on. So there's an x-axis and a y-axis, right? And so we kind of intuitively know what it means to be increasing, so something like that, right, on the interval there. And so the reason I know it's increasing on the interval that I can see is because if I pick any two x values, right, here's a, here's b, it's clear that the x value on the right has a larger y value that goes with it than the x value on the left does, okay? And so that's when you get increasing. So that's the reason that this definition makes sense. Right, and then of course the opposite is true for decreasing, right? So won't go through quite as many formalities here, but here's our axes, right? And so we intuitively know, decreasing function is one that's doing this, right? So as I move from left to right, the y values are getting smaller. All right, another concept we want to look at is the idea of a local maximum or a local minimum. So let's just kind of here we'll go ahead and maybe draw a quick set of axes. Sorry, that's a little bit off, isn't it? And so let's say I've got my graph that looks like that. Okay, so we would say this point up here, when I've reached the very peak of this hill, that is going to be my local max. And of course, then down here, when I've reached the bottom of this valley, that's going to be my local min. Okay, so it's literally just the top of a hill is the local max and the bottom of a valley is a local minimum. And then the last concept we want to look at is the idea of concavity, okay? And so I can also actually use the same sort of a picture as we had up here, but let's say I have let's draw one more set of axes here. Try to make my x-axis look a little bit better. Okay, and so I've got my function looking like this, okay? So when we talk about concave up, what we really mean is a good way to think of this is it's concave up if it would hold water. That's I think a nice way to think of concave up. So you can imagine over in here, I could pour water into here and it would actually hold water. Whereas in this part of the graph, if I poured water over it, it would just run down the sides, okay? Or another way of thinking of it is concave up is kind of the valley, right? Whereas concave down is this region where we're kind of forming this hill, okay? So we would say that this portion here is concave down, and then this portion down here is definitely concave up. All right, but obviously if we're concave down over here and we're concave up over here, somewhere in between we have to switch from one to the other. So what we want to kind of do is eyeball, when does it look like I've gone from having this downward curve to kind of transitioning over to this upward curve. And so we're just kind of eyeball it. It almost kind of looks like it's happening right at my y-axis here. So somewhere in here is that point where it switches. So that point where it switches from concave up to concave down is known as our inflection point. Okay. And it's worth noting that all of these concepts that we're looking at here, local max, local min, inflection points, concave up, concave down. These are all calculus concepts that you will study quite a bit when you get into calculus. For now, we're just going to familiarize with ourselves with the terms and use technology to help us find them. All right, so let's do an example here where we're taking a graph and trying to locate some of the important parts of this. So in part A, it says state the locations of any local maxima. Okay, so where am I at a maximum? Well, definitely up here, right? I'm at the top of a hill right here. Now my graph starts right here at 12, and you might think, well, that kind of looks like the top of a hill, but because there's no other side to it, we're not going to call that a local maximum. Okay, that's just kind of our starting point for this graph, and so the only local max would be here, and it looks like that's happening about x equals 4, so we'll go ahead and put that as our answer for part A. Locations of any local minima, well, definitely down here at the bottom of this valley. Looks like that's happening at x equals 2. And again, down here it looks like it's kind of bottoming out, but because there's no other side to this graph, we're not going to call that a local minimum. All right. Now we're going to state the intervals on which the function is increasing. Okay, so we're going to use interval notation just like we did when we were looking at the domains of functions. Okay, so we can see that it's increasing. Well, it's increasing between this minimum and this maximum. Okay, so what we would say is that it's increasing from 2 to 4. Okay, and we're using parentheses here because at the point of bottoming out or at the point of topping out, you're no longer increasing or decreasing. So that's why we're never going to include the endpoints in any of these intervals. Okay, so I'm increasing from the min to the max. And then I can look at where I'm decreasing. Well, there's two places, right? From the starting point down to the minimum, and then from the max to this ending point. So, of course, anytime we have two distinct intervals we're looking at, we're going to use our union notation, right? That glue that holds the intervals together. So what I would say here is we are decreasing from x equals 0 to x equals 2, and then we're picking it up back again at 4 and going to 6. All right, now it asks us to state the location of all inflection points, right? So those points where I seem to be transitioning between concave up and concave down. And really, I'm just kind of eyeballing this, but I am looking and it kind of seems like right here at x equals 1 seems like a pretty reasonable place to say that I've switched from concave down, so curved down, to curved up. Same thing here at x equals 3 and x equals 5. So those kind of convenient x values seem like pretty reasonable guesses as to inflection points. So I'm going to go ahead and list those out. X equals 1, x equals 3, and x equals 5. All right, and in part F, we're going to state the intervals on which the function is concave up. So once I've identified inflection points, I know that it's either concave up or concave down between those inflection points. So between this one and this one, I'm definitely concave up. So I can go from 1 to 3. But then I can also see over here it's concave up, right? So from 5 to where the graph ends at 6. All right, and then on what intervals is it concave down? Well, certainly seems to be concave down over here. So from where the graph starts at 0 to that first inflection point. And then between 3 and 5, it certainly seems to be curved down, so concave down. In this example, we're going to look at a function and find the intervals of increasing and decreasing and the intervals where it's concave up and concave down, but we're going to use technology to help us out with that. All right, so first of all, we're going to take a look at what this function looks like by typing it into our y equals menu. So we'll go ahead, x to the 4th. I'm going to hit my over button because if I forget to do that, it'll just continue to type stuff into the exponent. So if I kept typing from here, everything would be in the exponent. So I hit the over button as I write out these other terms. All right, so I've done that. And then let's just start by looking at your standard -10 to 10 window. So I could hit graph if that was the last window I looked at, but you can also hit zoom standard, and that will give you the -10 to 10 window. So with that, I can see the graph pretty well. But now let's think about what we did in the last example. In the last example, when we looked at intervals of increasing and decreasing, we noticed that we were really needing to find the local minima and the local maxima in order to figure out where it was increasing and decreasing. We also needed to find inflection points to know where it was concave up and then where it was concave down. So let's start by trying to find some of those important points. Now I feel like I can sort of see where our local maxima and minima are occurring, but it might be good to zoom in a little bit more. So if we go to window, and maybe switch it so that let's go between -3 and 3 in our x's, and maybe from -1 up to 5 in the y's. So -3 as my x minimum, 3 as my x maximum, -5 up to 5, and let's take a look at the graph there. All right, now I can maybe see a little bit better what's happening here. All right, so let's look for our local minima locations first. So local minima at, I can see I have 2 of them, so let's go ahead and find them. The place we're going to find them is by using this calc button, which is the second function of the trace button. So I'm going to hit second calc, go to number 3, which is minimum. Now it's asking for a left bound, so what that means is pick the minimum you're going to stab for. I'm going to go for this one down here first and get somewhere to the left of it. Doesn't matter really how far, just somewhere to the left and hit enter. Then it asks you for a right bound. Get somewhere to the right of it and hit enter. And then it asks you for a guess. Okay, so that just means kind of get in the neighborhood of your minimum, but it doesn't have to be perfect, and hit enter. And so what I get there is -1.44. Okay, so we have at x equals, and actually x is approximately -1.44. So we're rounding to the nearest hundredth here because these values are not necessarily nice values, so we're just approximating. So -1.44. All right, but I have another one, right? We also have this one over here. All right, so let's do that process one more time. Second calc, minimum. We'll get somewhere to the left of that minimum value. Get somewhere to the right. And then make a guess. And so it's telling me 0.69. So x is approximately 0.69. Okay, so those are our local minima. Local max, it looks like I just have one of those. All right, local max at x is what? All right, well, let's do the same thing, second calc, but this time choose maximum. All right, get somewhere to the left of the maximum, somewhere to the right of it, and then make a little guess here as we press enter. All right, now notice it's telling me 4.3796 e -7. Okay, so before we are too anxious to write that number down, let's think about what it means. First of all, notice it looks like it's at x equals 0, right? And then if we remember our scientific notation, 4.3796 e -7 means times 10 to the -7, which means take this decimal point and move it back 7 places. So what this number really is 0.00000043796. Okay, so we're getting this number that is very close to 0. And in fact, it's safe to assume that it actually is 0, because what happens is the calculator goes through an algorithm to find the maximum, and it is an approximate algorithm, okay? So it's using approximations, and so sometimes it doesn't quite land exactly on the true local max, but look how close it is. And if we're rounding to the nearest hundredth, of course, that rounds to 0. So we just go ahead and say x equals 0 is our local max. All right. And then with the understanding that we are increasing and decreasing, we're switching from increasing to decreasing at local maxes and switching from decreasing to increasing at local minima, these are the points that are really important. So if we go over to our graph here, it looks like from an x value of way over here, negative infinity, up to this x value of our first local minima, we are decreasing. So what we can say is that we are decreasing from negative infinity up to negative 1.44. And then we decrease again from the local max of 0, right, to the local max of 0 down to this local min, which is 0.69. All right, and then we're of course increasing on the other intervals. All right, so we're increasing from negative 1.44 up to 0, and then from 0.69 off to infinity. Okay, so those are the intervals where we're decreasing and increasing. All right, now concave up and concave down. So remember, that happened at inflection points. Okay, now I'm not going to I'm not going to have us use the calculator to really zero in on the approximate value of the inflection points, other than to just kind of have us eyeball it. So if we use this trace button, that allows you to kind of trace along the graph. And let's kind of eyeball here. It kind of is looking to me like the inflection point over here is kind of in this neighborhood somewhere. So maybe we'll call it negative 0.77. Okay? So it looks like we have an inflection at negative 0.77. Sorry, I should say x is approximately equal to negative 0.77. Sorry, I'll be a little cleaner there. And then we clearly have one, kind of over here somewhere. And it might not be a terrible idea to zoom in a little bit so you can see better. So let's say I did want to zoom in. Clearly I could really make this set of y values smaller. So maybe if I just do y values between 2 and 4, I would get a better view of what's going on there. And then I really only need x values, between 0 and 1, really. Okay, and so now I can see a little bit better. So if I trace along here, I could maybe have a little bit better idea of when it goes from being concave down to concave up. And, I don't know, this looks like a pretty decent guess here. How about this one right here? How about 0.386 or 0.39? So x is approximately 0.39. Obviously, we're doing a little bit of guesswork here. But then once we've determined those inflection points, okay, Let me go back to that previous window. Then I can, so where were we at? We were at -3 to 3. We were at -1 to 5, I believe, just so we can see the whole graph. Now we can better, we can go ahead and write out our intervals of concave up and concave down. So we are concave up. Concave up, well, looks like from -infinity to this inflection point, and that inflection point we decided was at -0.77. So -infinity to -0.77. All right, and then it's also concave up over here at this inflection point onto infinity. So we'll say from 0.39 to infinity. And then, of course, it's concave down in between those inflection points. Boy, I'm having trouble with my computer today. So -0.77 up to 0.39. Sorry about the screen jumping back and forth. I think the button on my pin's a little bit off. All right, one last example here. We're going to look at this function now and look at the intervals of increasing and decreasing. And we're going to not do the concave up and concave down for this one. So let's go to our y equals menu and erase our old function. Now I'm going to type this thing into y1, but let's understand that anytime we have multiple terms that we want to divide by something, we need to put those multiple terms in parentheses. So I'm going to start with parenthesis 1 minus x squared divided by x cubed. Okay, make sure those are in parentheses. All right, and we'll go ahead and start ourselves with a standard window. So go to Zoom, Standard. All right, and so we see that. Now, with the view that I have right now, it certainly looks like I have a little local max here and a local min here. Okay, but it's really hard to see the change in elevation. So this is one where I would probably zoom in on my y values by quite a bit. So I'll probably just leave the x's alone for now, but instead of going -10 to 10 in the y's, maybe do -2 to 2. And then that makes the whole elevation change much more clear. All right, so let's find those the min and the max first. All right, so my maximum over here on the left side, I just need to get to the left of it. Press enter to the left. Press enter somewhere to the right. Give it a guess. So it says -1.73. So we have a local max at x is about -1.73. So let's look for that local min. All right, so get to the left of that local minimum, get to the right, and give it a guess. And if you kind of study this function a little bit here, you may not be surprised that you just get the same value but positive as for the local max. So this is x is approximately positive 1.73. All right, so that's the only local max and local min, but on the other hand, I can see something interesting happening here, right? We studied the graph of 1 over x in class and talked about how when I had an x in the bottom of my fraction, I can't allow x to be 0. And we see the same thing here. This x cubed, if I plug 0 in for that, then I'm dividing by 0, which we know we can't do. So the function is undefined here. So one of the things we see with this example is it is possible to go from decreasing to increasing or increasing to decreasing when you cross an undefined portion of a function, and in particular when you cross a vertical asymptote is what we call this thing. And we'll study that idea of a vertical asymptote more later. But for now, just understand that when you see this kind of action on a graph, this could be a place where it switches from, in this case, decreasing to increasing. All right, so when I write out my intervals, I am increasing. Well, I'm clearly increasing from negative infinity up to that local max of negative 1.73. Okay? And then I'm increasing again from that local min of 1.73 up to infinity, right? Because definitely getting bigger there, just as over here I was getting bigger. Okay? Now decreasing, you might want to just say, well, oh, it's the rest of it between negative 1.73 and 1.73. Well, not so fast. It does start decreasing right after negative 1.73, but we have to stop it before it gets to 0, right? Because we know that the function is not defined at 0. And then we can also see it is decreasing over here as well, right? But we had to interrupt ourselves at 0, so then we just pick things back up after 0 and go up to 1.73. And so there are intervals of increasing and decreasing.